So hello everyone. So it's really a pleasure to be here in this wonderful event. So just a bit of a presentation. So I started to be interested in machine learning when I was a postdoc in London, UK, not London, Ontario. Because at that time my partner, she was basically a data scientist, so applying machine learning basically to esports. So her job was basically to watch esport games, and I thought it was kind of fun. So that's why I started to be interested, and then later to apply some techniques from ML to quantum problems. But now I'm more interested in the opposite. So let's say to use quantum devices for ML purposes. So, and basically my talk is mostly about these parametric quantum circuits that you have already heard about. And so the goal is to use a quantum device to build these parametric circuits and then do measurements on this device and use classical optimization techniques for several tasks, like a variational quantum eigensolver, QAOA, and some, let's say, more machine learning models like circuit board machines, QGANs, and so forth. So, so the reason why, so what I'm saying here is that these are one of the most promising applications for the NISQ, so the noisy intermediate scale quantum devices that are available right now and will be available in the future. But the N in the NISQ means noisy. And I think that here the role of noise is not much understood on how to tackle noise, how to tame noise for quantum optimization, and that's more or less the topic of my talk. So Nathan told me to avoid the conference-like format, so I thought that maybe I could start with some good old Italian movie. And that's the good, the bad, and the ugly. So let's say the good guy in our story is, of course, well, the quantum device. So the fact that we can exploit, so that we can exploit the quantum features of this device. But then, we are preparing, let's say, variational states and making measurements. So there is also the bad guy, is that we have to deal with stochastic outcomes from our device, and so we have to exploit them to solve our problems. But then we are using this for NISQ devices. So there is also the ugly, which is noise. So the noise from the noisy devices. And so if you remember, I don't know if you have seen this movie, but if you remember this movie, then you might remember that the ugly guy was not that bad, and and he was also kind of funny. And so somehow here I'm going to study the effect of noise, and my main message is that noise is not just something boring that is just there, but we can hopefully try to exploit the noise there. Okay, so that's basically the outline of the talk, so which is mostly focused on noisy parametric quantum circuits. So we have our goal, which is let's say to minimize the cost function, which is either the expectation value of some operator with respect to a parametric state, or let's say some distance between probability distributions, or some other quantity that we can calculate. And so we can use stochastic gradient descent for the optimization. But then, so the difference is that, so in an ideal quantum computer, so we prepare, let's say, a variational state, which is a pure state. So we initialize, for instance, our state in some reference 0. Then we apply parametric gates, so namely some unitaries, which depends on classical parameters, and we optimize over them. But let's say that since we have a noisy device, so this is kind of an ideal picture. So let's say a picture closer to the reality is that this state is prepared with some error. So it's like a mixed state. And there's this noisy, then this ideal gate here is applied with some noise. And then, we can describe this as a kind of quantum map. It's like a CP map, which depends on our parameter, and so forth. Now, this is still a very simplified picture, because if you really want to, you might have, for instance, no Markovian effects in this model, and then this description here is not that accurate. But we have to make some assumptions, otherwise we cannot do that much. And so now for the optimization, the vanilla gradient descent is that basically we follow this update rule, taking gradients of our cost function. But as you have learned from the previous talks, we can use a stochastic gradient descent. And in the machine learning literature, stochastic gradient descent is mostly about when you have a cost function which is a sum over many terms, and you just pick some of those terms, and then you update the gradients using them. But so the nice thing about parametric quantum circuits is that you can normally write the gradient of your cost function as an expectation value of some estimator g of j, which on average provides the gradient. So this means basically that g is an unbiased estimator of the gradient. And so the stochastic gradient descent and all other methods which are somehow variations of that basically follow this update rule, where you have, let's say, a noisy estimate, where here noisy means just because of quantum probability. So you have a noisy estimate of the gradient. And basically, people have studied this and found that you have very nice convergent properties, and even with the stochastic strategy, you converge to the local optimum. Now, there are also other algorithms, like the SPSA, so the simultaneous perturbation stochastic approximation, where somehow it looks a bit like a finite difference approximation, but is a bit more difficult than that. So basically, these quantities here, these deltas, are random variables. And if you carefully tune these random variables, then basically you get a biased estimator of the gradient. But the bias is quite small. And it has been shown that this algorithm converges and basically also converges to a global optimum of the cost function. So it seems that here you introduce extra noise via these parameters in order to somehow escape from local minima and then go to the global optimum. So then, I mean, you might start arguing, then is noise either good or bad? Of course, we come from a quantum information background, and so noise for us is always bad. We would like to correct that noise. But if we use NISQ devices, then I mean that's not possible. And then there is also the point of view for the classical optimization guys, where I mean noise can be good for something. And indeed, for instance, when you simulated annealing or other of the stochastic algorithms, you introduce noise in order to stochastically jump from the local minimum and possibly achieve the global minimum. So, I mean, we used a very simple idea back in 2016 to basically we introduced noise. At that time, we were interested in problems like compiling a certain target unitary using some parametric quantum evolution of a quantum system. And our cost function was basically a fidelity. Well, yes, the infidelity is the cost, but which is written as an average over, let's say, the different states with respect to the possible initializations. So this average can be done exactly, and the resulting fidelity looks like this. So where you see this is not convex. So you have the global maximum and some local maximum. But somehow, if we sample from these states and we calculate this cost for each sample, then depending on the sample, you might see that the cost doesn't have this local maximum, and you can escape from this, let's say, non-optimal points. So this is one example where basically introducing some extra noise was actually helpful for the optimization. So I mean, the message here is that noise, in some sense, can be good. But then why do we have to add extra noise? Here we have a lot of fluctuations. So in NISQ, so in parametric quantum circuits, we have fluctuations coming from quantum physics. So if we prepare a variational circuit and we perform measurements, then we are going to get results depending on different probabilities. But then if we have also an implementation of this scheme using NISQ devices, then we also have like other fluctuations coming from the imperfect gates that we apply. So can we somehow exploit these fluctuations in some way? Now, so I mean, this is all very, so I'm mostly a theoretical physicist, so I mean, what I'm presenting is somehow theoretical bounds rather than numerical results. I will also show you some numerical results. But basically, what you can find is that, I mean, you can run many simulations, but you can also ask yourself, I mean, you can ask a fortune teller whether you're going to be lucky with your numerical simulation or not. And I mean, this can be made precise using basically convergence properties of stochastic gradient descent. So these properties are kind of well known in the literature of stochastic optimization, but that literature is quite hard to grasp. So there are two papers which are written in a more quantum language, one by Harrow and Knapp, and a recent one by Streke, Maria, and others, where they also discuss the convergence of stochastic algorithms for variational problems. And you observe some convergence like this, where I is the number of iterations of your gradient update rule. And so, so the difference between your estimate of the optimum value and with the true one somehow decreases with the square root of I. And G is a quantity which basically describes the variance of the gradient estimator. So this makes sense because somehow if you have a gradient estimator which has a very large variance, then in principle you should expect a slower convergence. Right, but then so we have a problem. So how do we get an unbiased estimator G for the gradient when we have noisy operations? Okay, so let me give you some examples. So if the ideal gate can be written like this, so it's like so we have a parameter theta and some operator hj. And suppose that for some reason, so because we are lucky, we can write our noisy implementation of this gate in the quantum device as some noise that happens before and is independent of theta, plus then the ideal gate, plus some noise that happens after the gate. So if that's the case, then everything that you have seen so far still works. So you can use the parameter shift rule, you can use other methods to measure the gradient. And for instance, one case where you have this sort of noise is when, for instance, is in your device, if you tell the machine to somehow to rotate, so to apply a gate which depends on a parameter theta, but this parameter theta might fluctuate in your experiment. And if this fluctuation follows like a Gaussian distribution, then you can integrate over noise and go back to this picture. So if this sort of noise is the dominant source of noise in your experiment, then everything basically works. So you can write gradient estimators using parameter shift rule or a Hadamard test and so forth. But there are cases where you're not that lucky. So for instance, if you consider a slightly more physical model of what's going on in your device, like even a simple Markovian evolution described by a Lindblad equation. This is a very simplified model again for a noise. For more involved things, so for more accurate things, you can also read a nice book by Francesco. But even when you have this simplified noise model, it's not clear, at least to me, maybe to some people in the audience here it's clear, but it's not that clear to me then how we can write a parameter shift rule or other things like the Hadamard test. So they might provide some biased estimator of the gradient. So here it's just a circuit of the Hadamard test. So what can we do then? So basically, we wanted to study a bit of the convergence time, and something that we can always write. So even though we don't know how to take, let's say, how to write, formally estimate the gradient, so we can always use the tools from the quantum information geometry, which tells you that because of the properties of quantum states, when you take a derivative of a state, you can always write it as a symmetric logarithmic derivative. You can always write it in this form, where L here is called the symmetric logarithmic derivative. And so once you have this, this thing here, you can write a theoretical gradient operator, which looks like this. And that basically, in the case of pure states, can be, you find basically the usual the usual commutator thing that you know. So this, I mean, now you can, in principle, measure this operator here and get an estimator for the gradient. Okay, so, but then also something that we found very recently, and maybe will appear on the archive very soon, by the end of the week, for instance, is that now you can also find a bound on this quantity here, which depends on a quantity, which is used in quantum estimation theory, which is the quantum Fisher information. So this thing tells you, links somehow two different aspects. So the part about optimization to the part on estimation. And so now you can see that even though we don't know in principle, I think it's still an open question how to measure efficiently gradients when you have the noisy regime. So we can use our knowledge from quantum estimation theory, and basically we know that the quantum Fisher information decreases as a function of the noise strength. So you see that noise can also has a positive effect here, namely that of reducing the amount of fluctuations in your gradient estimator. But then noise, of course, has a negative effect, basically which increases the cost. The cost means that your cost function now is noisy, so it's going to be larger. Okay, but then basically we found some numerical examples, and in some cases we found that basically noise can actually help even in numerical simulations when basically you have a small number of shots. Okay, so this is just I want to recap here. Is that so we found this bound here on the convergence time in terms of the maximal quantum Fisher information. And so my main message is that noise is not something boring, but you have to exploit noise already when you write equations in order to understand how to deal with it. We don't know whether noise is fundamentally helpful in some regimes. And then I think the main message here is that whether we can design better optimization algorithms that fully exploit quantum fluctuations in order to optimize these functions. And one possible perspective is to use the natural gradient, which somehow includes already the information about the QFI in the optimization procedure. So this is a very recent paper by Nathan, Josh, and others. But I think here, I think an open question, at least for me, I don't know for you guys, is still how to write this update rule when you have when we have open systems. But I think this might be one of the way to design better optimization algorithms that work that fully exploit quantum fluctuations. Okay, so how much time do you have? 2 minutes. Okay, let me go very quickly then to something which is the beyond NISQ. So when we write these parametric quantum circuits, so we have again a circuit like this, but we can also rephrase this in this language of a quantum processor. So somehow we have a quantum processor which reads a classical register, and then depending on the values that are read from here, applies a different operation on the input. And okay, so then the idea is that okay, so maybe we can also make these parameters here described by quantum states. And if we do something like that, so here is again, so again, it's similar to the neural networks. Again, you are training. So the goal for training is to learn these classical parameters. Now, if you use this processor sort of thing, then the goal is to learn this quantum state here. And so if you do that, okay. So if you do that, one of the very simple things that you get for free is that quantum states are a convex set. So when before here you had a cost function which looks like this. So when you have quantum parameters, everything is nice and convex. And then here also you can, I will skip all of this because I don't have time. But then again, you can generalize the gradient descent, to something which is a quantum gradient descent, namely that somehow it updates all the times the state of the quantum program. But here we still have the open question is how to define a cost function such that this G superoperator mapping states into state can be efficiently computed. So I just leave you with this. I mean, this is just an open question also for you guys. And so with this I conclude. So I basically discussed about NISQ, quantum optimization, showing that basically the convergence time of stochastic gradient descent can be bounded by the quantum Fisher information. And so using this bound, you can show that noise can help during the initial steps. And then beyond NISQ, I mean, we can also do optimization of quantum parameters. And when you do that, you get for free that you have a convex problem. But there's still an open question how to, derive a suitable cost function which is simple enough in the update rule. So with this, I think I conclude. And thank you for your attention.
Thank you for the talk. And you say that for the Fisher bound, your Fisher information lowers with the noise, right? But you have to invert it. So don't you ever come into problems where it gets unstable and just blows up because you invert a very small number?
You mean for when you use
the natural gradient descent?
I think that's a very good comment. Well, I don't know that, but even when we have open systems, I even don't know how to get that quantum Fisher information matrix. So in the paper by Nathan, Josh, and others, they found that basically the diagonal part of that quantum Fisher information matrix can be efficiently sampled, right? But when you have open systems, I don't know if you can avoid having to calculate the L operator via the symmetrical logarithmic derivative, and I don't know any efficient way of doing that. Right. So to answer your question, is that so maybe when you try to estimate that quantity, you won't get something which is that small, and yeah.
I just like you had the slide when you were talking about the difficult noise, and then you had this this how to construct an unbiased gradient. An unbiased estimator of the gradient there. So is this, I didn't really get, is this practical? So do you now mean if I've got a noisy system, I should do it this way? Or is this like a theoretical, was this a theoretical observation?
So the thing about the L
operator?
Yeah. I think that, in my opinion, well, at least that's the way we use that, is mostly as a way of getting bounds, okay? Because if we, so that L operator is basically what you know already when you have a pure state. So it's basically, well, again, you obtain the anti-commutator thing. But when we have open systems, then basically you have to get that L operator by solving the SLD equation. And I don't know how to do that. And so, and I think that's an open question. And so, yeah.